Kia ora and welcome technology teachers to this screencast about technological modelling. The scope of this screencast is to unpack the key messages from the national markers on Achievement Standard 91612, demonstrate understanding of how technological modelling supports technological development and implementation. Achievement Standard 91612 or 3.5 is a Level 3 achievement standard. This screencast is part of the Secondary Student Achievement Professional Learning and Development Initiative and is funded by the Ministry of Education. This screencast is one of a series related to the externally assessed technology standards which can be found on our technology wiki sites. This screencast is also available to download as a PDF with additional notes. My name is Pippa Lawler, and I am one of a team of technology facilitators working together with teachers throughout the country to raise student achievement. You, like me, will be keen to discover the key messages, but first we need to position this standard in relation to some strategic documents which inform teaching and learning. In preparation for teaching and learning, there are a few key documents that teachers need to be familiar with. In this section, I shall highlight some of the most important references and areas where teachers can find in-depth support and detailed information that will inform teaching and learning. Achievement Standard 91612 is at Curriculum Level 8 of the New Zealand curriculum. The objective is concerned with how students use critical analysis to judge or determine the role that technological modelling had in the development and implementation of a technological outcome. In relation to the New Zealand curriculum, Achievement Standard 91612 belongs to the technological modelling objectives in the technological knowledge strand. At this curriculum level, students are expected to understand the role of technological modelling as a key part of technological development. This includes justifying its importance on moral, ethical, sustainable, cultural, political, economic and historical grounds. At curriculum level 8, guidance about technological modelling is available in the Technology Achievement and Learning Objectives. The appropriate section can be found under the Technological Knowledge strand under Section 8-1. Teachers can support students to develop a critical and informed understanding of why technological modelling is an important aspect for ensuring that responsible and defensible decisions are made during the design, development and any subsequent manufacturing of technological outcomes. One way this can be demonstrated is for students to undertake a reflection of their own technological practice. Alternative methods would be for students to analyse a case study or undertake an investigation into the technological modelling that has been applied in someone else's practice. The technological outcome has to have been implemented, placed in situ and tested, that is, developed to the prototype or one-off outcome stage. In terms of the NZQA website, resources available to teachers can be found on a subject-by-subject basis. It's a good idea to bookmark your subject pages for easy reference. On this particular subject page, information is grouped into 3 areas: generic technology, construction and mechanical technologies, and processing. All resources relating to generic technology are grouped together. This includes levels 1 through to 3 and both internally and externally assessed standards, and thus resources relating to Achievement Standard 91612 are located here. When students have a clear understanding of the task and they are confident in the use of technical language and terminology, they will be most successful in producing a clear and concise report. In this section, I highlight some of the pre-learning that needs to take place. Technological modelling is the testing of design ideas to see if they can contribute to a fit-for-purpose technological outcome. There are two types of technological modelling: functional modelling, which is the ongoing testing of design concepts, and prototyping, which is the realisation of a fully functioning model. Taken together, the two types of modelling provide evidence of factors that may impact on and consequences that may arise from the development of a technological outcome. The key step up at curriculum level 8 is the consideration of competing and contestable factors. Competing factors are those that are in direct opposition, and therefore only one can be chosen to be put ahead of all the others. Ultimately, this means that only one can be accommodated, or one must be prioritised over the other, or one actually overrides the other or generally outweighs the other in a selection process. Competing factors that students may readily identify within their own practice are time versus quality, where students are working to strict time constraints, or cost versus quality, where students are working with a limited budget. Typically, priorities are compared to a specification and ranked. Ultimately then, one priority will become the most important and influencing factor for decision making. Contestable factors are those which can be disputed. Choice could be challenged as there is always more than one viewpoint. Compromise can be accommodated in a design, but the priority and importance will vary with stakeholder views and are often based on people's roles, viewpoints and values. These factors may arise from a number of issues, which will include, but are not limited to, ethical, social, historical, cultural, political, economic, sustainable, humanitarian and environmental. Some factors may be highly contestable, and others perhaps less so. For example, if we look at the issue of culturally appropriate design, we might ask the question, who decides on the culture and its appropriateness? This is dependent on values and viewpoints. Another example would be to look at environmentally friendly materials and ask the question, to what extent are they really green? This example uses a student project of a robotic window cleaner to help explain how technological modelling involves two kinds of reasoning. Firstly, functional reasoning provides a basis for exploring the technical feasibility of the design concept and the realised outcome. That is, how to make it happen in the functional modelling phase. And the reason behind how it is happening in prototyping. The example shows a range of modelling, from 2D drawings to a 3D construction model and a digital program, all of which were steps the student followed as they worked towards producing a working prototype. As prototype is the modelling of a realised but yet to be implemented technological outcome, the purpose of prototyping is to evaluate the fitness for purpose of a technological outcome against the brief and to establish, or not, a defensible case for its implementation, refinement, or further development. Practical reasoning is concerned with the questions of, should we make it happen, and should it be happening, in consideration of a range of factors, including moral, ethical, sustainable, cultural, political, economic, and historical grounds. Technological modelling makes use of both functional and practical reasoning to provide a holistic evaluation of a technological outcome's potential and its likely impact on the world. Technologists often use specialised language and symbols to communicate specific information about technological modelling. Students will need to be familiar with specific vocabulary and terminology which is relevant to the technological products they are evaluating. The key terms and explanations are more deeply explored in the Level 1 screencast relating to technological modelling. This is at Level 6 of the New Zealand curriculum and relates to Achievement Standard 91048. The screencast by Cheryl Pym on technological modelling specifically relates to Level 7 and supports student achievement in the external assessment for Achievement Standard 91358. Either or both of these could be a useful review point. They can be accessed through our technology wikis. All students need planned opportunities to learn, use and practice the specialist vocabulary that is vital for academic success. Since technological outcomes involve diverse materials areas, it is essential that students can access authentic contexts. This is most often likely to be their own technological practice. However, in order to develop critical thinking, teachers can encourage students to develop a broader awareness of technological outcomes through case studies and other forms of reflective practice. These three very distinct examples of student prototypes help to illustrate how the physical and functional nature of any outcome will depend upon the materials used, since they will contribute to how that outcome appears and performs. Is it worth spending time on vocabulary instruction? Students may need support to understand the specialist language both of technology and of the materials area within which they operate. They also need to know technologically specific words and terms relating to the standard in order to develop their use of language and in-depth thinking. The key areas of understanding to focus on for this standard are competing factors, or in other words, actual competitive factors, and contestable factors, otherwise defined as potential competition. It is worth spending some time with students in order to differentiate between the two and create the basis for clear understanding. In this section, I will highlight the requirements of the standard by exploring a selection of student work from previous years. I will focus on comments from the national markers, which indicate what students did that enabled them to achieve success. Step-by-step analysis helps to break down exactly how students met the achievement criteria at all levels, including merit and excellence. Unless otherwise noted, all the extracts, including images, are taken from NZQA exemplars, which are available to download and span the period from 2012 to 2015. This screencast just provides a brief snapshot, and teachers would want to access the full reports and exemplars in order to give their own students formative feedback. The assessment report comments on good practice. This includes the basic layout and structure of a report. Most schools find that A4 is a convenient size on which to send their submissions. There is a page limit, and students must ensure they work within the limit. Only the first 10 pages of evidence can be marked, and therefore larger submissions will provide no additional advantage. Students would do well to focus on quality, not quantity. Successful candidates produced reports which had clearly headed sections. For example, competing and contestable factors, functional modelling, testing and trialling, and prototyping. Candidates who use these types of headings and then reported to the requirements of the standard with accuracy and directness are the candidates who enjoyed success at all levels of the standard. Successful candidates also cited references correctly. A quality report would include evidence of student voice, genuine evidence of testing which has been applied to the material choices for the outcome, and a successful link between a case study and student practice. Students who gained achieved in this standard did so by successfully demonstrating the following 4 aspects. Firstly, students were able to differentiate between functional modelling and prototyping in relation to the process of developing a technological outcome. They could give examples of this in their own technological practice. The coloured text highlights examples of student voice using key phrases. In this example, the student used the modelling of the toile as a method of evaluating fitness for purpose. The modelling enabled them to evaluate the design and make informed decisions to proceed to the prototype stage. Secondly, successful students were able to look at their outcome and identify some relevant competing and contestable factors involved in the creation and/or the use of the outcome. They then went on to explain which of these specific factors were being tested by the modelling. In this example, the student resolved the contestable factors involved in considering form over function. When considering materials, they investigated only those materials which could be cut using a CNC cutter, and in doing so, identified how the material properties contributed to ways in which it can be shaped and formed, and how this would impact on the design of the prototype. As a further result, they were able to explain how modelling can be used to address the competing and contestable factors identified. Thirdly, successful students showed an understanding of the relevance of modelling at different stages of technological practice. In this example, the student has identified that the calico chosen for the initial toile or fabric model did not have the stretch properties of the final material selection, but that modelling at this stage allowed them to check for fit and to model the garment in a 3-dimensional way. Students often modelled aspects of an outcome in different ways, for example 2D and 3D, showing that they understood appropriateness of modelling techniques at various stages of development. Finally, there was evidence and explanation of how the modelling identified has informed or influenced decision-making during the development and implementation of an outcome. In this example, the student carried out a test print for technical feasibility. As a result of their testing, they identified that although they were able to work with close tolerance, they didn't get the result they desired. And so they changed the size of the printing mesh they were using to achieve the desired outcome. They have further identified that modelling and functional reasoning help them to manage risk. Teachers may find that it helps their students if they can provide some advice as to how a report may be structured and what some of the key terms mean. Students might need some assistance to understand that in order to achieve the standard, an explanation of practice is needed, not just a description of practice. Similarly, defensible decision-making can be defined as that which is rational and based on research and facts. Teachers may want to help students by suggesting they use a pre-writing guide. That is, something which can be filled in prior to starting to write and can be used to gather notes, reflections and photos throughout the project. Encourage students to write in their own voice, as this helps with authenticity, and provide feedback to students throughout the process. In this section, I will look at what else students need to do in order to gain merit. Successful students demonstrated 5 further key qualities in their reports. Students who achieved with merit demonstrated different forms and evidence of modelling. Students explained in depth the different forms of modelling used as a development progressed, as well as the nature and relevance of the evidence that the modelling provided. At this level, a paragraph of succinct and precise information allowed the student to provide a detailed explanation which demonstrated their understanding. Links made between modelling and development also made explicit connections between decisions made during the development and the results of the modelling practices carried out. Explanations included detail on how specific competing and contestable factors were addressed by the modelling. Students correctly identified and defined competing factors as those which could be rank ordered. Successful students wrote about how they decided their priorities. In this example of student writing, the student prioritizes sustainability as a key factor and justifies her subsequent decision-making by referencing sustainability. The examples the student gave were specific and related to her own practice. Contestable factors are those where choice can be challenged. Early on in her own practice, this same student identified that stakeholders might hold a different opinion and chose strategies for dealing with potential conflict. Bear in mind that it's possible to look at everything with a different lens, and opinion is always contestable. Successful students were able to explain how the changes they made in the planned development of an outcome were related to and as a result of the functional modelling they had carried out. In this example, the student was undecided as to whether to incorporate a hood or a collar or either, as all of her stakeholders had different opinions. She made a toile of the garment with a collar and asked stakeholders to try it on and give her feedback. Then she unpicked the collar and replaced it with a hood and repeated the process. As a result of modelling, she found that the collar interfered with the wearing of a cycle helmet and gained feedback that the hood was a useful accessory. Together, this informed her decision as to how to develop the outcome. Successful students reflected on what was changed or what could be changed during the development phase as a result of what they had discovered through prototyping. In this example of student work, they describe how they tested the different shapes of arm and shovel intended for use on their remote-controlled vehicle. As can be seen from the quantity of student writing, testing was thorough and considered each of the options from a number of different performance specifications. The rigour of the testing produced a rich set of results, which allowed the student to comment on their findings and reflect in detail. Successful students made explicit links between the decisions made during the development of their outcome and the results of the modelling carried out. In other words, they were able to identify and justify how, why, and at what stages changes had been made. In this example of student writing, the student clearly highlights how they were able to gain a broad selection of information through modelling. They further identify that modelling was carried out at strategic points prior to prototype development, and that due to timely intervention, the feedback enabled them to minimise risk management. The step up to excellence requires students to provide more analysis and detail. Successful students are reflective and critical of their own practice. They also draw on case studies and the practice of others to illustrate key ideas which may not have otherwise have occurred within the limitations of their own practice. Typically, they demonstrated 3 further things that set their work apart at this higher level of achievement. Successful students were able to explain how key factors were resolved through modelling. As well as identifying diverse forms of functional modelling, they explained how modelling might be modified over a period of development time. A well-structured, comprehensive and reflective discussion would detail how both functional modelling and prototyping have influenced the development of an outcome. This could be from their own practice or that of others, since students often used additional expertise in order to gain further relevant information. In this example of a food project, the analysis and reflection ran to several pages. However, the student justified important factors and defended their inclusion, so there was no padding, just detailed explanation of the many and comprehensive considerations. Students were able to explore a wide variety of issues relating to competing and contestable factors. Their explanation showed that they correctly differentiated between the two. Analysis showed clear understanding of the difference between competing and contestable factors. Discussions were robust, and the arguments put forward reasons as to how decisions were defendable and justifiable. Students made good use of case studies to exemplify their points. Lastly, in this section, successful students achieving with excellence provided a comprehensive and reflective discussion showing how technological modelling and prototyping influence the development of an outcome by giving valid reasons for specific decision making. Technological modelling was shown to defend and validate those decisions. Successful students were able to justify their choices of modelling at various stages in product development in relation to their chosen context, and typically used testing and trialling to resolve any areas of contestability. However, they were also able to identify the limits of their own testing and trialling, drawing upon expert comparisons and industry practice through case studies. In this example of student work, the student partnered with a client company trialling a yogurt formulation for infants for export to China. The student carried out extensive technological modelling in many different ways, involving groups of stakeholders. The final report was data-rich, presenting additional information in graphical ways which enable the student to analyse it with clarity through their discussion. In this section, I shall signpost further points for consideration and other resources and activities that may offer guidance. The Technology Teaching and Learning Guide supports senior secondary students by providing teachers with a framework to enable students to succeed. Key NZQA documents will provide up-to-date information and the latest commentary empowering teachers to guide students to success at all levels. As these documents are renewed and revised annually, it is essential to work with the most recent versions. Look for the most up-to-date exemplars on the NZQA website by using this link. It's often useful to backtrack for a few years in order to pick up recurrent problem areas or trends that the markers will then highlight in their reports. The marker comments may be brief, and you might find it easier to gain insight when you take the time to unpack the exemplars as we have done in this screencast. This could even be a deliberate activity that you choose to do with your students, perhaps to help them identify the structure of a report, or identify elements of good practice, or find examples of competing and contestable factors. When you carefully select good examples to share with your students, you will be modelling for them what success looks like, and emphasise what must, should, and could be included in a report. In this way, students will have clear guidelines to work towards positive achievement success. That brings us to the end of this presentation. If you have any questions regarding issues raised in this screencast, I recommend that you contact the appropriate technology facilitator for your region to seek further clarification. Thank you for your participation. Ka kite and goodbye.